Have you ever wondered how your phone just knows your password? Or how a video game saves your progress right where you left off, even after you turn it off? It really feels like magic, doesn't it? Well, it's not. It's actually a really clever trick of logic. And today, we're going to pull back the curtain and show you exactly how it works, starting from the very beginning.
I mean, really think about this question. With an old spinning hard drive, you could kind of picture it, right? A little arm writing data onto a spinning platter. But your phone? Your laptop's solid-state drive? There's nothing moving in there. It's just a silent piece of silicone. So how in the world does it remember anything? That's the exact puzzle we're going to solve.
And the answer starts right here, by understanding that pretty much all digital circuits can be split into two big categories. Getting this one distinction is the absolute first step to unlocking the secret of memory.
Okay, this is the perfect way to think about it. On one side, you have combinational circuits. These are like a doorbell. You push the button, that's the input, and it rings. The second you let go, it stops. The output only cares about what you're doing right now. It has zero memory. But then you have sequential circuits. These are like a light switch. You flick it on and it stays on, long after you've taken your hand away. It remembers what you did last. That ability to remember its state, that's everything.
So, to put it a little more formally, a sequential circuit's output doesn't just depend on what's happening now. It also depends on its own history, what its state was a moment ago. And the way it does that is by combining simple logic gates with something new, storage elements. Those storage elements are the secret ingredient we're looking for.
So how do we build one of these storage elements? Well, we're going to start with the simplest, most basic form of memory you can possibly make. It's a little circuit called a latch. This is our very first attempt at storing a single bit of information.
And here it is, the SR latch. S stands for set, and R stands for reset. Just think of them as two simple commands. You send a pulse to the S input and boom, the latch's output becomes a 1. It's now set. You send a pulse to R, and just like that, its output becomes a 0. It's been reset. And the really cool part? When you're not telling it to do anything, it just holds on to whatever value it had last. It remembers.
Okay, let's just walk through this. If S and R are both 0, it holds its state. Perfect, that's what we want. If you make S a 1, it sets the output to 1. If you make R a 1, it resets the output to 0. This is all working beautifully. But hang on a second. Look at that last row. What happens if you try to tell it to set and reset at the exact same time? What does that even mean?
Yeah, that last row. That points to a really, really big problem.
This is the fatal flaw. It's called the undefined state. When you tell the circuit to be both a 1 and a 0 at the same time, it basically has a digital panic attack. It doesn't know what to do. And that kind of ambiguity is absolute poison for a computer system that needs things to be perfectly predictable. You just can't build anything reliable on a component that might just break down.
So, of course, engineers came up with a really clever solution, the D-latch. What they did was brilliant. They took the original SR latch and made a simple but critical change. By adding an inverter that links the set and reset inputs, they made it physically impossible to send a 1 to both at the same time. If one is 1, the other is forced to be 0. Just like that, the fatal flaw is designed right out of the circuit.
Okay, so we've solved the reliability problem, but that creates a new one, timing. In a modern processor, you have billions of these components. You can't just have them all changing their state whenever they feel like it. That would be absolute chaos. You need a conductor to lead this digital orchestra, and that conductor is the system clock. This brings us to the edge-triggered flip-flop. This little circuit has a superpower. It only pays attention to its inputs for an infinitesimally small moment in time. The exact instant the clock signal ticks, or what we call the rising edge. At every other moment, it's completely ignoring its inputs. It's got its ears plugged. This is what ensures that all billion components in a system act in perfect synchronized time. Now, to make this work, there are a couple of very strict rules. The first is setup time. Think of it like taking a photo. The data you want to store has to be held perfectly still for a tiny moment before the shutter clicks, before that clock edge arrives. This gives the circuit a chance to get a clear look at the data.
And the second rule, as you might guess, is hold time. Sticking with our camera analogy, the data also has to stay perfectly still for a brief moment after the shutter clicks. You can't have your subject move while the picture's being taken, right? Together, setup and hold time guarantee a perfect, crystal clear snapshot of the data is captured on every single tick of the clock.
All right, so now that we have this incredibly reliable, perfectly timed memory element, we can start to specialize it. Just like a mechanic has a whole set of different wrenches for different bolts, digital designers have a toolkit of different flip-flops for different jobs.
And here's the main family. The D flip-flop, that D stands for data, is your basic workhorse. It's perfect for just grabbing a piece of data and holding it steady. Then you've got the JK flip-flop, which is more like a Swiss Army knife. You can configure it to do all sorts of things. And finally, you have the T flip-flop. This one's a specialist. T stands for toggle. Its only job is to flip its state from 0 to 1 or 1 to 0 every time the clock ticks. That simple on-off action makes it perfect for building things like digital counters.
Okay, we've been way down in the weeds of logic gates and timing diagrams. Let's pull the camera all the way back now and look at the big picture. How does this one tiny circuit become the billions of bits of memory sitting in your computer right now?
Well, it all comes down to this one number.
Every single thing we've talked about, the latches, the clocks, that fatal design flaw and the clever fix for it, all of that incredible complexity is in service of one single goal, to reliably store a 1 or a 0, a single bit. And from that one bit, everything else is built. You group a few of these flip-flops together, you get a register. You arrange billions and billions of them on a silicon chip, and you get your computer's RAM. This simple clock circuit we just dissected, it is the fundamental atom of our entire digital world.
So, now you know the secret. It's not magic, not at all. It's a beautiful, cascading waterfall of pure logic, starting with a simple circuit that couldn't make up its mind and evolving into a perfectly timed system that our entire modern world runs on. So the real question is, now that you understand this fundamental building block, what will you build with it?